Salam afternoon, Doctor.
Alright. Alright, how are you today? Semua macam lemau je ke apa?
Sihat, Doktor. Sihat.
Sihat. Alhamdulillah.
Sihat, Doctor.
Alright. So, saya doakan semua dipermudahkan segala urusan sama ada urusan pelajaran ataupun urusan whatever urusan lah yang kita ada dalam kehidupan kita ni.
Amin.
Ya, amin. Okay, 38. Alright, so today is the last topic for the something like something went wrong. This is okay, sorry. Something wrong. Okay, let's start again. Alright, so today is the last topic in the chapter 3, which is time response. And this is the last part, which is the overall the main thing that we're going to learn in a control system, because the title of this course is control engineering. So this is the control part. Okay. Okay, before we start, let us recap what we have learned so far in time response chapter 3. Chapter 3, time response. Right, in the first part of the chapter 3, you learn how to derive time response equation. Right, so you do all the steps there. Then you get the time response equation, which is in terms of yt equal to something. Okay, so you already did that. Okay, and then the second part we learn about classification. Right, this is a small topic there, classification. We'll be able to classify a control system into several classification group. Right, and then the third one we learn about first order system. Right, so in first order system we learn about the transfer function of first order system and how the parameters in the transfer function will affect the behavior of the first order system. Okay, so the transfer function is k over 1 plus ts, and then we learn about k, gain, and also t, which is time constant. Right, and yesterday we learned about second order system. Oh no, not yesterday, right? Yesterday is the is it yes on Tuesday, 2 hours on Tuesday, we learn about second order system, where the transfer function is k omega n square over s square plus 2 zeta omega ns plus omega n square, where the parameter that we're going to calculate is percentage of MP, rise time, T1, T2, settling time. Right, so we have learned about the equation to calculate all these parameters. Right, and also on Tuesday you learn about steady state error. Okay, so you learn about we have steady state error 1/1 plus Kp or 1/Kv or 1/Ka. That is depend on the type of different input. Okay, and then you also learn about the open loop transfer function, the class of the open loop transfer function. All right, so to summarize that what you have learned, okay, so we actually learn about, okay, let's say it is second order. Okay, the first part is to get the equation yt equal to something. All right, and the second part is to learn to calculate, okay, tr t1 t1 kat sini, t1 t2 ts and the percentage of. Okay, so I also explained about I also explained about transient region and steady state region. All right, so meaning by now you should be able to get the equation for the time response equation for any system, and then you will be able to analyze whether it is at the transient region or at the steady state region. Okay, so the steady state region is steady state error. Okay, why for the transient? All these parameter here, and I choose second order system as the example. All right, so let's imagine, okay, you have a system. Okay, you have a system. Don't know, maybe let's choose a spring damper system. Okay. Okay, we have the input xi, and then we want to see how the displacement at this point here. Okay, so and then we apply unit step input. Okay, so of course when we design, we have some requirement. Okay, we said maybe one is in terms of how fast the response of the system. And the second one, that is for the transient region, because this is first order system. And the second one is steady state error. All right. So we have some specification on that, right? And then we apply the input to the system, right? So we apply the unit step input. Let's say this is the input, blue one. This is the input. Oh, okay. Not recorded there. Sorry. I forgot to record. Okay. All right. So let's say this is the input UT, right? So we want the system to go into one, right? However, when we apply the input to the system, okay, suddenly the system only behave like this. Okay, so it may be satisfy the first requirement, not satisfying second requirement, or it may be satisfy the second requirement but did not satisfy the first requirement. Okay, as in the example, we can see there is some steady state error, and then maybe no, maybe here is the time constant. Okay, so this is a system where you already design, you already choose the spring, you already buy the damper, and then you put together, then you apply, and suddenly the behavior of the system is not what you want. Okay, so if this happen, okay, we're not going to change the spring, we're not going to change the damper. Okay, meaning we're not going to buy a new damper, we're not going to buy a new spring, because we know that the value of K and damper here will affect the behavior of the system, right? So somehow, maybe due to the disturbance, due to the some element that you haven't considered in the system, when you assemble the component, okay, it does not behave like what you want. Okay, so instead of changing K and C, meaning buying new spring, buying new damper, okay, normally people won't do that, okay, because it will involve big cost there, because you need to buy new components. Okay, so instead of doing that, what we're going to do is we're just going to add a controller. Okay, so the controller, okay, so here we come to here. So instead of having input apply direct to the system and get the output, okay, so we're going to add a controller. Okay, so instead of having system and get Y, apply U, all right, you apply that, then you see the behavior is not as what you want. Okay, so in order to repair the behavior or to improve the behavior of the system, or to improve the response of the system, what we're going to do is we're going to add a controller. Okay, so the objective of this controller is to improve the response of the system. Okay, if the response is too slow, then by adding controller, it should be able to improve in terms of the time constant. It should be able to make the system respond faster. Or if it is in terms of a steady state error, okay, for example, you buy an oven, you set 180 to bake a cake, but suddenly when you measure the temperature is only 150. Okay, there is a 30 degrees Celsius error. Okay, so by adding a controller on the oven, we will be able to improve the time response, and also in terms of the steady state, we should be able to reduce the steady state error there. Okay, so that is the function of controller. Okay, so the controller that is added to a system should be able to improve whether it is first order or second order system. So if it is first order, it may be in terms of time constant and steady state error. If it is in terms of second order system, you'll be able to improve in terms of oscillation, rise time, settling time. Okay, so we need to choose a suitable controller for our system such that it will improve the response here. All right. Of course, there will be, of course, there are many type of controller that we can use. Okay, nowadays it is popular with AI, so you maybe have heard about artificial intelligence, deep learning. Okay, all that is type of controller. You have intelligent controller, you have a neural network, which is a kind of deep learning deep learning controller. Okay, maybe you have a traditional controller like predictive controller, robust controller, adaptive controller. Okay, or the most simplest one that we're going to learn today is a PID controller, or just a simple gain controller. Okay, so there are many type of controller. Okay, but we're not going to learn it all. Here we're just going to focus on the PID controller because PID controller is the most popular controller that we use in the industry because it is simple. It is very simple, and it is not complex. Okay, there is no additional component that need to be added. Okay, it's just a parameter. All right, and yet it is successfully to improve the statement. Sometimes the system sometimes better than any other complex controller. Okay, some of system may able to produce a better controller if you use a complex controller, but most of the time PID controller is sufficient enough. All right, so how to apply PID controller? Okay, so PID controller is just a parameter actually. Okay, so first let's understand the concept of a feedback controller here, where you can see that the input to the controller is error. Okay, you can see the difference between desired output or our setting, and compare with the with the actual output. Okay, so it gives us error. So for that, this kind of controller is known as error-driven controller. Okay, meaning the control action, the control signal MS there will be calculated based on the error. Okay, so if the error is big, then the control action will be bigger lah. Okay, if the error signal is small, then the control action will have small effect on the process there. Okay, so meaning the input to the controller is error, right? So for a PID controller, it's just a combination of 3 components, which is P. Here is D, and this one is I. Okay. Okay, if you look at the P part here is equal to KP, where KP is just a value. Okay, KP can be 0.5, which is not amplifier, it's get the signal smaller. KP can be 1, KP can be 2, KP can be 10, 100, 1,000, 500, any values actually. Okay, so okay, by having a proportional gain, which is P controller, okay, it will be able to improve the system performance. Right? So later we can see that by adding a P controller into the system, okay, you can see the response of the system will improve, and then it will also able to reduce the steady state error. Okay, basically for class 0, okay, the steady state error cannot be eliminated. Okay, we have learned that on the Tuesday on the table we can see for class 0, applying unit step input, the error will be always 1/1 plus KP. Okay, so the error can be reduced, the value of the error can be reduced, but we cannot eliminate the error. Okay, so there will be always a value, very small value, but still there is a steady state error. Okay, so that's why we said P controller cannot eliminate steady state error. So we cannot eliminate it at all. We cannot get 0 error. Okay, so in terms of transfer function, okay, okay, the transfer function of the P controller is only a value KP. We call that as a KP, but it is actually a value again. All right, that is for P controller. And then for the second part is I controller. Okay. Just now it said that for class 0, okay, the steady state error will always occur, and by using only P controller, we cannot eliminate the error. Okay, so if you refer to the table, previous one. Okay, I think I already explained that in order to have 0 error, okay, so class 0, okay, class 0, we have error, steady state error. Okay, but if you change the system to become class 1, okay, you can see that the error will become 0. Okay, so this is related to the integral action. Okay, if we look at the transfer function here, the integral action is Ki over S. Okay, so let's say that our system is 1 over S plus 1. Okay, 1 over S plus 1 is class 0. Okay, the last term here is number, so it is class 0. All right, that is for the system. Okay, the system without any controller. But now since we already add a controller into the system, we need to multiply with the controller. Okay, you refer to the block diagram here. So for the open loop transfer function, for example, it is K, G, H. So we're going to multiply K with G and H. If it is for the open loop transfer function. All right. So therefore, the transfer function, okay, will equal to Ki over S plus 1. Okay, so we can see here the transfer function now has become class 1. Okay, class 1 due to the highest highest order of factorial S is 1. Okay, so now it's become class 1. So we can expect that the error will become 0. Okay, so now we change the system from class 0 to class 1 by adding integral control action, because the integral control action have Ki over S. So the 1 over S term here, S at the denominator. Okay, so that's why the system become class 1. So we can expect the error will become 0. Okay, so that is the effect of integral action. It will be able to eliminate the steady state error. If your system is class 1, okay, it's easier to explain using the table here. Okay, if your system applying step input and your system is class 0, by adding integral action, the system will become class 1, then you get 0 error. Right? If your system is applying ramp input and you cannot, of course, you cannot apply to class 0 because it will become infinity. So your system should at least class 1. Okay, you should at least class 1 for a ramp input. Okay, if you apply a ramp input into class 0, the error is infinity. So we know that the system will become very unstable. It will damage the system. Right, so at least for a ramp input, your system should be at least at class 1. Okay, so the error will be 1 over kV. Okay, so in order to eliminate the error for a ramp input, you need to change to class 2. So this also can be done by adding integral action. 1 over S will become multiply with what? A system. multiplying 1 over s, it become class 2. So therefore, we can predict the system will provide 0 error. Okay, same goes to the class 2, 1 over Ka. So you need to change to class 3. So it will give you 0 error. Okay, so that is the function of integral action. Okay, all right. Okay, the last component. Okay. Okay, the last part in PID controller is derivative control action. Okay, so in terms of transfer function, it is KDS. Okay, so the function of derivative here is to predict the direction of the error, because by differentiation, well, if you differentiate, you actually get the gradient. Okay, so if your error, for example, we plot the error function ET, right? So the error is, I don't know, maybe like this. All right, how the error change with time. Right, so by if this here, all right, so we get the gradient. So the gradient is negative, so we know the error is toward, meaning it getting smaller. All right, but at this time here, the error is positive, then we know that the error is getting bigger. Okay, so by knowing the derivative part of the error, we will be able to predict the direction of the error, and therefore we can take action before the error occurs. Okay, and if you can see that KDS here, if you multiply to the system, okay, so the S term will be at the numerator. Okay, the S term will be at the numerator, so it will not affect at the denominator. So that's why it will not affect on the performance of the system for the derivative part. All right, so that is the 3 term. So you know the transfer function. P part is only Kp, then integral part is Ki over S, and the derivative part is KdS. Okay, so normally I and D is not used standalone. We not use only D controller. Okay, we don't use only I controller. Okay, so normally we have a combination of PI controller. Okay, but P controller can be standalone. Meaning you can just have a P controller only. Okay, because it is only a gain. So we can have P controller only. Okay, but not I controller or a D controller. Okay, but instead we need to combine P and I, PI controller, or P and D, PD controller, or a combination of all 3, PID controller. Okay, so this is the transfer function for the PI controller. Okay, this is basically coming from KP controller plus the I controller, which is Ki over S. Okay, so from the equation you get this equation here, right? Where Ti is actually Ki over Kp, Kp over Ki. Okay, Kp over Ki. Okay. Ki is what? Ki apa nama dia? Saya dah sebut tak? Ki is integral gain. Kb is a derivative gain. Kp is the Kp is displacement gain, takkan? Kp is what? proportional gain. Okay, KP is proportional gain. All right. So that is the transfer function for PI controller. All right. And then the second one is the transfer function for PD controller. Again, it is coming from KP plus KDS. Okay, so from there you get a KP multiplied with 1 plus TDS, where TD is KD over KP. Okay. All right, or a combination of all three there. Okay, KP plus KDS plus KIS. So we have P, we have D, and we have I. Right, but the standard name is PID controller. Okay, so this is the transfer function for a PID controller. So you need to remember the transfer function of this type of controller, whether it is P controller, PI controller, PD controller, or PID controller. All right. So by knowing the transfer function of a PID controller, we can see that it only depends on the KP value, which is proportional gain, KD value, derivative gain, and KI value, which is the integral gain. Okay, so meaning we need to choose the suitable value for KP, KD, and KI. Okay, so choosing a value is what we call as tuning. Okay, so normally we've said we need to tune the parameters for PID. Okay, so that is actually means that you need to choose a suitable value, a combination of PI and D, so that the system will behave as what we want. Okay, as our specification. All right, so during my days when I learned about this controller, okay, during my master project, I did my master project on the PID controller. All right, we need to, at that time, in order to choose the value of PID controller, I need to try and error. Okay, I change the value of P, I, and D and see how the performance. And then I try a few, many combination in order to get a good response as possible. Okay, as based on my objective lah. Okay, so I have the objective for my system. So I tune the parameters. I try and error doing that until it satisfies my requirement. All right, but it's quite difficult because you have many combination. Sometimes you put bigger P, smaller D, smaller I, meaning you have lots of combination, 0.01 up until 10,000, 100,000. Okay, so there are many combination there. Okay, so so another way you can do is you can use Ziegler-Nichols method. Okay, at that time I have not learned about Ziegler-Nichols method. Okay, but Ziegler-Nichols method is actually a structured way of how we can tune the parameters rather than using try and error method. Okay, Ziegler method, the method is quite similar to try and error, but it is in structured way. Okay, meaning there is a step. Step 1, you need to tune this until a certain condition. Okay, then you follow with the KD parameter until it receive until it produce some kind of response. Okay, and then you continue with KI until you get the parameters that you want. All right, that is during that time. It's around around 18 years ago. Okay, 18 years ago. I think I remember. Yes, 18 years ago. Okay, I did my master there. All right, but nowadays it is easy. Okay, the field of tuning the controller is not a research field anymore. Okay, because nowadays we have a MATLAB toolbox where it's allow us to tune automatically. Okay, So we supply the transfer function to the system, okay, and then we ask that to tune that automatically. So automatically it will provide us response, okay. So then we just need to adjust the requirement, okay, so that the MATLAB will provide the response that we want. Okay, so it's quite simple. All right. Right. So that is the concept that you need to understand in control. Okay, where we should understand that a controller is added to a system in order to improve the response of the system. Okay, so by having a response, it depends on your requirement. Okay, it depends on the design of the system. All right, so one of the popular method, simple method, popular method and sufficient method is PID controller, where actually we just need to adjust 3 parameters, okay, KP, KI and KD, so that the response of the system will provide the response as per specification. All right. All right, so let's do the example. Okay, so in the example, I hope you will be able to understand more on the effect of adding controller to the system. Mana nak gerakkan? Right. Okay, example here. Okay, it said a first order control system with unity feedback. Okay, I hope you already understand. If I said unity feedback, it is a feedback there with 1. This is feedback. Okay, this is the feedback. And the value is 1. The transfer function is 1. So that's why we call that as unity feedback. Okay. It's already mentioned it is a first order system. Okay. So we can expect the transfer function will be in first order. All right. So this is the system. All right. And then we add a controller. Okay. And we're going to test with 3 different controller. Okay. First one is when controller is P controller equal to 1, equal to 2. And second one is only P controller again, but the value is higher, which is equal to 9. And then here we have a PI controller. Right? So we need to sketch the time response of the system when we apply unit step input when T equal to 1. So this is the T. So T equal to 1. All right? Okay. So first step, what you're going to do? What is the keyword for your first step? What we're going to do here?
Sketch.
Anyone have idea? Yes, Amirul Hazim.
Sketch.
Sketch. So how to sketch? Okay, yes, it asks us to sketch the time response, but the keyword is actually the time response. Okay, so you should remember when it is related to time response, we should get the open loop or closed loop. Is it open loop or closed loop transfer function? Closed loop or open loop? I believe I already mentioned this before.
Close.
Yes, Amirul, thank you. It is closed loop transfer function. All right. So for time response analysis, we're going to get a closed loop transfer function. So the first step is to get closed loop transfer function for the system. All right. So let's us consider because here we have A, B, C, and D. So let us consider number 1 for the systems alone without adding any controller. Okay, or the controller here is 1. All right. So okay, let's just consider there is additional controller here, which is apa, A dah ada 1 lah kot. GCS equal to 1. Okay, the gain is 1. So if the gain is 1, meaning it is actually only the system itself. Right, so for the closed loop system itself, so we have G closed loop transfer function will equal to 1 over S plus 1. 1 over S plus 2 lah. Okay. This one will become 1 over S plus 1. So if it is kg, is kg over 1 plus kgh. Okay, so it is 1 over S plus 1 over 1 plus 1 over S plus 1. So you get 1 over S plus 2. Okay, that is when the gain is 1, meaning without any gain. Gain is 1 is tak ada gain lah tu kan. Alright. Okay, for A it is for A the gain is equal to 2. So it will become 2 over S plus 1 divided by 1 plus 2 over S plus 1. That one will give you 2 over S plus 3. Okay, so this is the transfer function when the controller is equal to 2. And then you can do for B and C. So for B, you should get 9 over S plus 10. Okay, you have 9 over S plus 1. 1 plus 9 over S plus 1. Okay, should get you 9 over S plus 10. And the last one we have PI controller. Okay, 2 plus 2 over S multiply with 1 over S plus 1 divide by 1 plus 2 plus over 2S, K, and G is 1 over S plus 1. Okay, so you will get 2S plus 2. 2S plus 2 divided by S plus 1 divided by 2S S square plus 2S plus 3S plus 2 there, plus 2. Okay, which is we over the same. Then we'll be able to cancel that. Should be able to cancel this part here. Right. Okay, let me continue up here. So the equation will become 2S plus 2 divided by S square plus 3S plus 2. But then you can do the S plus 1 divided by S plus 1, S plus 2. Okay, so we'll be able to cancel that. So lastly, the transfer function will become 2 over S plus 2. Right, so that is the closed loop transfer function for PI controller. Okay. All right. Let's say S1, S plus 2, 2S plus 3, 9 over S plus 10. Right. So let's do it here. All right. So A1, when the gain is equal to 1, so the transfer function, let's just use K, transfer function ni lah G. Panjang nak tulis banyak-banyak. Okay. So the transfer function is equal to 1 over S plus 2. Right, that is when G equal to 1. Then we have A here, when the G equal to 2, the closed loop transfer function will become 2 over S plus 3. Right, and B, the transfer function is equal to 9 over S plus 10. And then the last one for C, the transfer function is equal to 2 over S plus 2. Okay, all right. So by looking at the closed loop transfer function, so from the first step we determine the closed loop transfer function, and we do know that this system is first order system. All right, so we don't for the first order system we can get the value of K and T by comparing to the general transfer function 1 over 1 plus Ts. Okay, so in order to get that, right, so you need to derive this by 2, divide this by 2, divide by 2, divide by 3, divide by 3, divide by 3. Divide by 10, divide by 10, divide by 10. This one divide by 2, divide by 2, divide by 2. Okay. So, alright, so what will be the value? Okay, so the new closed loop transfer function will become 0.5. Okay, 0.5 over 1 plus 0.5s. Right, and this one here will become 0.67 divided by 1 plus 0.33, 1/3 kan. Alright, and then here for this one here we get 0.9 divided by 1 plus 0.1s. And for the last one, it will become 1 over 1 plus 0.5s. Okay. All right, so from there we'll be able to determine K and T. Okay, so this is K. And this part here is the time constant. All right, so let's put that into a table. Okay, let's put that into a table. Okay. 1, A, B, C. Okay. First, let's determine for K and let's determine for T. Okay, so we can get, okay, please tell me what is the value for K for system 1?
0.5.
0.5.
0.5. The time constant is it 0.5?
0.5.
Yes, 0.5. Okay. And the time constant is 0.5. Right. Okay, for A is 0.67. 0.67.
33.
Okay, for B is 0.9. Here is 0.1. Last one is 1 and then it is 0.5. Right. So that is the value of K and T. Right, you already know that the K value will give you the final value. Okay, we can calculate Y final is equal to K multiplied with U. Right, so our U here is U equal to 1 because it is unit step input. Right, so we can calculate for Y final. Okay, so because unit step input is 1, so basically is the K value only, right? So it is 0.5, 0.67, 0.9, and 1. Okay, meaning after reaching steady state, it will reach this value. Okay, it will stable at this value. All right. One more thing to calculate before we can sketch is y at time constant. Okay, y at time constant is equal to 0.632 multiplied with y final. Y final. Okay, so please calculate 0.632 multiplied with 0.5. Okay, I know this one. This should be 0.632. Okay, 0.632 multiplied with 0.5.
0.316.
0.316 multiplied with 0.67.
0.423.
0.423. And then 0 multiplied with 0.9. 0.5.
569.
57. Okay. All right. And then additionally, you can also calculate the steady state error. Okay, the steady state error is equal to 1 minus y final. Okay, 1 minus y final. Okay, so for this one, we expect 1, but it only able to stable at 0.5. So therefore, the steady state error is 0.5. This one here is 0.33. This one here is 0.1, and this one here is 0. Okay. Okay, so now we can sketch. Okay, let's do the sketching. So this is just a sketch. So don't expect to have a good looking graph. Okay, this is YT. All right, what is the highest value? Let's consider. Here is 0.5. Then okay, here is 1. All right, let's say here is 1. So therefore here is 0.5. Right. Okay. For system A, okay, for system when there is no controller, okay, it will reach 0.5, and for the time constant, it will reach 0.316. Right, so the value of time constant is 0.5. So at 0.5, it should reach 0.32. 0.32, where is it? So here is 0.25, so around here. Okay, that is my sketching. Right, I just predict that. Okay, around somewhere there. So it is 0.332, right? Okay, and then it will reach the final value around 0.5. Right, around here. This line lah. Okay, so if I able to plot the response, so the response will be like this. Okay. All right, so that is when there is no controller to the system. Only you apply the input, feedback, still feedback system, but no additional controller directly to the system. Okay, so that's it will behave. It will take 0.5 seconds to reach 63.2% of 0.5, and then it will stable at 0.5. All right, let's sketch for number 2. Okay, number 2 is when you apply gain controller equal to 2. All right, so it should reach 0.67. The time constant is 0.33. 0.25. Okay, 0.25. So 0.33 is around here. All right, and then it will reach 0.423. 33, so around here lah. And then the final value is 0.67. 0.7 something, 0.67 kat sini lah. Right? 0.67. Okay, so if we get sketch, then it will get something like that. Okay. All right. So you can see that by adding gain equal to 2, we're able to improve in terms of time response, because we can see the time response is reduced. Okay, instead of taking 0.5 seconds, it's now the time constant becomes 0.33. All right. And then in terms of steady state error, all right, without any controller, the steady state error is 0.5, meaning the error is 0.5. And then it reduced to 0.33 after you change the gain to 2. Okay, so you can see that by adding the effect of P controller, by adding P controller, you'll be able to improve the response of the system. Okay, and second one, you'll be able to reduce the steady state error. Right, let's plot number 3, which is B 0.9. So it should reach 0.9. Right, 0.9. Should draw the line for 1 here. Right, and then it should reach 0. The time constant is 0.1. Okay, 0.1, 0.25, 0.1 here. Right, and it should reach 0.57. 0.57. Yeah, lebih kurang. Right, so if we plot the response, okay, so it should get this kind of response. All right, so by increase the P controller, we can see that the response is become faster. Okay, now it takes 0.1 second, and then it also reduce the steady state error become 0.1. Okay, from 0.5 becoming 0.33, and then becoming 0.1 when we increase the value of P controller. Okay, you can still increase the value. You can put 10, you can put 100, but you can still see the steady state error. Okay, the steady state error will always be there, and then after some time you cannot see the changes in the time response anymore. Okay, so we're going to compare the response when we add a PI controller. Okay, PI controller is for C. Okay, so it will be reaching 1. Okay, it will be reaching 1. And then the time constant is 0.5. So it should reach 0.632. So 0.632 is around here, bawah sikit pada 0.67. Right, so the response will become okay, so it's just a sketching. Shape dia tak not very accurate, but basically we can see, right, by adding the PI controller, now we can see that the steady state error is equal to 0. Okay, no steady state error anymore because it reached what we want, 1. Okay, but we can see that the time response is now slower. Okay, so you can improve that by tuning the value of PI controller. Maybe you can try with 9 plus 9 over S. Okay, you can check that to see whether the response will be improved or not. Alright, so I will let you to do that if you want to see that kind of response. But of course, you can expect the response will also reduce. Okay. Alright. Okay. So that is the effect when we add a P controller to the system and PI controller to the system. Okay. This example is choose because it is able to we'll be able to do that manually. Okay. If you choose other system, let's say just now I said if you can check with 9 plus 9 over S, basically it will become second order system. So second order system will require you to calculate more parameters there. Okay, but you can expect there will be overshoot and etc. Okay, because the system has become a second order system. Okay, so you should be able to conclude that by adding P controller, you will be able to improve the response of the system and reduce the steady state error, but cannot eliminate the steady state error. Okay, the steady state error can only be eliminated by adding I action, integral action. Okay, and then you can tune that in order to get the response that satisfy your condition, your requirement. Okay, thank you. If you have any question, you can ask. If you don't have, you have class after this, you can leave. Right?
Doktor,
Yes.
test 1 sampai mana?
Okay, for test 1, basically I haven't got any info from other lecturer, but based on previous semester that we always discuss, it should be covered up until second order system. So the question may be first order system or maybe second order system. Okay. Okay, so basically we have cover chapter 3. All right. After the semester break, we start with chapter 4, which is the stability. You are section 9 and 10, right? Okay, so meaning I will stop until here. Okay, because after the semester break, Dr. Zahar Hamdi will take over this class. Okay, section 9 and 10, and you is 9 and 10, yes. 9 and 10 and 7 and 8. So that 2 section will be taken over by the Dr. Zahar Hamdi. I will only teaching 15 and 16. 15 and 16. All right, but we still have 1 more week. For next week, we're going to do the MATLAB and Simulink. Okay, I will show you how to use MATLAB and Simulink in order to draw a block diagram, to simulate the behavior of any system in block diagram or using transfer function, and also do the time response analysis, or maybe if we have time, we can do the auto tuning PID controller. Okay, and then I will give you a project that will be based on the MATLAB Simulink. Okay, so that one is next week. I will share the link for you to download the MATLAB or use the MATLAB from the UTM for our session next week. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Thank you, Doctor.
Doktor.
Thank you, Doctor.